Good afternoon, everybody. We're from Group 21. I'm Sebastian Wirnanda Pehri, and with me are my group mates Cornelius Daryl and Jonathan Kurniadi. Today, we'll be presenting about a statistical performance analysis of hallucination detection algorithms for large language model. Now, for the abstract, LLMs or large language models have shown strong capabilities in understanding and generating natural language. However, they still tend to produce some hallucinations, which are responses that sound convincing but are actually false. This is critical, especially when LLMs are used for sensitive areas such as healthcare, law, education, etc. Though hallucination detection methods have been proposed, their performance often varies depending on the dataset and evaluation setup. Now, this study here aims to analyze and compare several detection approaches in order to see which models would have the best result. Now, for our problem. Obviously, first and foremost, the increased use of LLMs highlights the importance of ensuring the reliability of their output. However, hallucination remains a major issue as they can generate false information. As a result, it remains unclear which hallucination detection approach consistently performs the best across different datasets and evaluation conditions. Now, for our objectives, we have four, which is the first one, evaluate multiple hallucination detection methods. Secondly, compare their performance using statistical metrics. Third, identifying the most reliable one. And lastly, analyze the performance. Now, for methodology, the study adopts a quantitative experimental approach to evaluate and compare multiple hallucination detection methods using standardized datasets and comparing several representative detection approaches to provide a broad understanding of their strengths and limitations. Our metrics here are as follows: precision, F1 score, recall, ROC, and MCC.
Okay, so next on the methodology, we have data use. For the datasets, we use truthful Q&A, hallucination eval, and fact score. For the models, we are using contradiction-based, retrieval-based, self-consistency, uncertainty-based, and internet state. Decoding on the internet neural states, this dual configuration ensures our empirical tests are both comprehensive and deeply representative as the modern detection capabilities. So these are the results based on the hallucination category. We have the detector section and then factual error, also with summarization error and creative hallucinations. We observe the factual errors remains relatively across all evaluated detections. However, when transitioning to creative hallucinations, performance can increase across the board, notably the factual error, summarization, and the hallucination. So the self-consistency spikes to a noise point 70, showing its vulnerability in open-ended generative environments. Next. Alright, in here we have the overall performance, like over 100 bootstrap interactions from the methods we use, and then precisions, recall, F1, OROC, and MCC. In the internal signal detection on struggles on the achieving an F1 score of only 73.03%, this strongly suggests that cross-referencing external facts is vastly superior to interpreting a model hidden activations. On the Shapiro work, normality test on the bootstrap F1 score distributions, we have the same as the methods, and then statistics, p-value, and distributions. Normally, tests on our F1 scores look closely at the table number 3. We see that self-consistency, internal signals have like all yield p-values on the well above, across 0.05 threshold, confirming the normal distributions. However, uncertainty-based detection fails the normal assumption with the p-value and the W statistics. Because of this mix of non-normal and the normal data, the parametric tests are inappropriate, guiding us to a directly non-parametric alternative. Next. Alright, this one is the post hoc pairwise Mann-Whitney. This one is just like the before, but instead of methods, we use pairs, and then with U, also with another p-value, and the significant In here, we can see each pair of the consistency shows is it significant or not, also with the U value and the P value. The consistency versus uncertainty, which can cause the detecting LLM hallucinations, kind of error or approach in different like approach.
Now moving on to F1 score by hallucination category. Let's look at how the four methods perform across different hallucination categories, namely factor error, summarization error, and creativity hallucination. For factor error, the retrieval base once again lead with a F1 score of 86.34%, followed by self-consistency at 81.07%. Interestingly, for summation error, uncertainty base actually come out on top with 84.48%, slightly higher than retrieval at 83.70%. Meanwhile, in the creative isolation category, all methods show a dropping in performance, with uncertainty base becoming the lowest at 68.83%, while retrieval remained the most stable at 81.58%. This shows that no single method consistently outperforms the other across all hallucination type varies and depend on the casuistic of the error being detected. Now we in the ROC curve and coefficient matrix slide. Here we present the ROC curve for all four methods to examine the trade-off between true positive rate and false positive rate. Retrieval base produce the curve closest to the top left corner with a AUROC of 0.94 indicate the best overall classification performance, followed by uncertainty at 0.91 and self-consistency at 0.89 and internal signal at 0.85. On the right, we show we show the conclusion metric for retrieval as the best performance method. Out of the total data, this method correctly classified 545 fractured case and 333 hallucination case with a relatively small error of 68 false positive and 54 false negative. Now, in the sensitive to the text notion level slide, we also test how sensitive each method is to the noise level, comparing a low noise best case condition against the current noise profile. Under low noise condition, all methods perform significantly better and more uniform, with retrieval staying consistently above 93% across all categories. However, as noise increases to the current profile, we see a very significant drop in performance across all methods, especially in creative hallucination category. This demonstrates that robustness to noise is an important factor, and relative base show the strongest resilience compared to the other methods as the data become noisier. Now, in conclusion, based on this control statistic benchmark, we found that retrieval-based classification is the strongest and most consistent detector, achieving a F1 score of 84.56% and AUROC of 94.41%. Meanwhile, self-consistency and uncertainty-based detection show no statistically significant difference in performance with a p-value of 0.49. On the other hand, inter-signal probing performs significantly worse than the other methods with a p-value of less than 0.001. This finding comes that retrieval-based or externally verified approach outperform methods that rely solely on the model signal.
Okay, so that is all for our presentation. Hope you've learned something useful with our presentation, and we hope to see you again maybe someday or next time. That is all, and thank you for listening.